Picture this. It's late. You have your IDE open, dark mode is on, the rest of the house is totally quiet, and, well, you're staring down a system prompt.
Yeah, we've all been there.
Right. And you're building an AI feature. You've just tweaked the instructions to make the model sound, a little more professional, a little less robotic.
The very common tweak, sure.
So you run a quick test. The output looks great. You push the change to your staging environment, and, well, the next morning, you realize that while your model now sounds incredibly professional, it has completely forgotten how to format JSON correctly.
Oh no, the classic downstream break.
Exactly. It's returning markdown blocks, it's hallucinating keys, and basically breaking your entire downstream pipeline. You fix one thing and you broke something entirely unrelated. It's basically the software engineering game of whack-a-mole, but with AI.
It's a deeply frustrating experience, and I mean, it highlights the exact reason why building robust AI applications feels so fundamentally different from, traditional software engineering.
Because the rules are just entirely different now.
They are. In traditional coding, you write a unit test. The function either returns true or it returns false. You assert that 2 + 2 = 4. It's binary, and more importantly, it's predictable.
Right. I can rely on it to behave the same way every time I run the test suite.
Exactly.
Yeah.
But when you're dealing with large language models, the output is non-deterministic. It's highly variable natural language. The architecture itself is stochastic. So, how do you write a unit test for nuance?
You really can't, right? I mean, not with traditional assertion.
No, you can't.
Yeah.
How do you mathematically prove that version 2 of your prompt is like 20% more helpful than version 1 without breaking the JSON schema?
And you certainly can't just sit there and manually read 10,000 test outputs every time you make a commit. I mean, unless you have an infinite timeline and a massive budget to pay an army of human testers.
Which none of us do.
Right. So that brings us to the mission for today's deep dive. We're looking at the core problem every engineer faces when building with AI right now. How do you actually measure quality at scale without going bankrupt?
And the solution we're extracting from our source material today is a concept called LLM-as-Judge. Basically, using AI to evaluate AI.
Which sounds a little wild at first.
It does, yeah. But it represents a fascinating shift in the engineering paradigm. We're moving away from hard-coded logic tests into probabilistic evaluation.
So today, we're really going to explore the mechanics of how this automated grading actually works under the hood.
Right. We'll look at the economics driving the adoption, the hidden, frankly, very human-like traps that these models fall into when they play judge, and most importantly for you listening, the specific engineering solutions you can implement in your CI/CD pipeline to make this grading system reliable.
Let's unpack the core premise here, because on the surface, it sounds almost circular. Like, if I don't trust my primary LLM to always get the answer right.
Which is why you're testing it.
Exactly, which is why we're testing it in the first place.
Well,
so how on earth can I trust another LLM to reliably grade it? What is the fundamental mechanism that makes an LLM a competent judge of another machine's work?
well, the underlying logic comes down to a concept we can define as the asymmetry of AI. The core factual premise here is that judging quality is simply easier than producing it.
Easier how? Like computationally?
Yes, computationally and structurally. Think about the cognitive burden of generating a perfect, novel response from scratch. The model has to synthesize information across its neural network, maintain strict grammatical structure, ensure factual accuracy, and hit a highly specific tone.
And it has to do all of that sequentially, right? Token by token.
Precisely. That requires massive traversal of its latent space. But evaluating a piece of text that already exists, that requires far less heavy lifting.
Because the text is already there in the context window.
Right. Because of this structural asymmetry, a strong model can reliably assess and grade text generated by weaker models, or even text generated by itself on a previous run.
If we map this to traditional software engineering, it sounds a lot like the dynamic between a junior developer and a senior engineer during a pull request review.
Oh, that's a really good way to think about it.
Right, like when you're the junior dev tasked with writing a complex new system from scratch, you have to hold the entire architecture in your head. You're worrying about dependency injection, edge cases, the syntax, the performance.
It's a huge cognitive load.
Exactly. It might take you 3 days to write 500 lines of code. But then you submit the PR and the senior engineer looks at it. They don't have to write it from scratch. They just have to scan the diff.
And within 5 minutes, they can point to line 42 and say, hey, this loop is going to cause a memory leak.
Right. So it's that exact dynamic.
It's a strong visualization, though. With one important technical caveat, a senior developer actually understands the logic and the underlying business rules of the code.
Oh, right. The LLM judge doesn't actually understand anything.
Exactly. It doesn't understand the code or the text in a human sense. It's executing incredibly high-level pattern matching to spot anomalies against its training distribution.
Okay, that makes sense. But practically speaking, the dynamic holds up for the workflow.
It does. In the AI workflow, the senior engineer is your judge model. That's usually a highly capable, large parameter model running offline.
And the junior developer?
That's your application model, which is likely a smaller, faster, heavily quantized model optimized for low latency in production. You use the heavy, expensive model asynchronously to review the pull requests of the smaller model.
Generation is computationally hard, but discrimination is relatively cheap. That totally tracks. But, if we're trusting the senior engineer AI to be the ultimate arbiter of what goes into production, we really need to understand its blind spots.
Oh, absolutely.
Because if our testing pipeline relies on a flawed judge, we aren't just failing to catch bugs, right? We're actively optimizing our application for the wrong metrics.
Yes, and this is where the deployment gets incredibly complicated.
Yeah.
You cannot just pass an output to an LLM, prompted to grade this response, and blindly trust the integer it returns.
Right. Our sources point out some very specific systematic biases that plague these LLM judges.
They do. The source material highlights two major systematic biases built into the architecture of these models that you have to actively engineer around. The first one is position bias.
Position bias. I assume this comes into play when you ask the model to compare two distinct outputs, like routing response A and response B into the prompt and asking which is better.
Precisely. When you present an LLM judge with two options side by side in the context window, it exhibits a strong, statistically significant preference for whichever response appears first in the prompt.
Really? Regardless of the actual quality.
Regardless of the semantic quality of the content. If you run the prompt again and simply swap the exact same texts, so the original response B becomes response A, the judge will frequently flip its decision and pick the new response A.
Okay, we have to dig into the why there. Why would it just blindly favor the first thing it reads? Is that like a flaw in the training data, or is it something fundamental to the architecture itself?
It's largely an artifact of the transformer architecture itself, specifically how the attention mechanism operates.
Okay, how so?
Well, transformers process tokens in parallel, but their attention heads often assign disproportionate weight to the tokens at the very beginning of the context window. It acts as a cognitive anchor.
So it literally latches onto the start of the string.
Yes, the model uses those early tokens to establish the context for everything that follows. Consequently, the first response heavily biases the subsequent generation path, making the model mathematically more likely to validate the first set of patterns it encounters.
That is a massive structural flaw if you're trying to build an impartial grader. I mean, it's literally anchored to the presentation order. And what about the second bias mentioned in the sources?
The second is verbosity bias. This is the tendency of the LLM judge to prefer longer responses simply because they are longer.
Wait, really? Just raw word count?
Basically, yes. Even if a shorter response is concise, accurate, and perfectly answers the prompt without any hallucination, the judge will often assign a significantly higher score to a sprawling, multi-paragraph response that contains repetitive filler.
It's actually funny how incredibly human those flaws map out to be.
How do you mean?
Well, when you describe position bias and verbosity bias, I instantly picture a tired human teacher grading a massive stack of term papers at midnight on a Sunday.
Oh, that's a great comparison. The behavioral parallel is definitely there.
Like, think about the position bias for a tired grader. The teacher picks up the very first essay in the stack. Their brain is fresh, they are paying attention, and they think, wow, this is pretty good, solid A.
Right, they have the energy to engage.
Exactly. But by the time they get to the 20th essay, they're exhausted and just skimming. So the first thing they read gets the benefit of the deep analysis. And then the verbosity bias is just the oldest trick in the book.
Writing a 10-page paper for a 5-page assignment.
Exactly. A student doesn't really know the answer, so they just write 5 pages of absolute fluff, hoping the sheer weight of the paper will trick the teacher. And the exhausted teacher just looks at the thickness of the staple and assumes effort equals quality.
It's a very relatable analogy. And, while the human teacher does it out of fatigue, the underlying mechanism in the LLM operates on pure probability.
because it's just predicting the next token.
Right. LLMs are, at their core, next token predictors. A longer text contains more tokens, more context, and typically more structural markers of a comprehensive answer. Things like transition words, bullet points, or concluding paragraphs.
So the judge model equates that density of linguistic tokens with quality.
It registers the structural effort and rewards it, entirely missing the virtue of concise accuracy.
Okay, so if I have these two massive architectural biases working against me, a judge that anchors on the first thing it reads and rewards sprawling word counts, how do I build a testing pipeline that doesn't just automate my own failure? We have to engineer the bias out of the system.
We do. And this is where we transition from understanding the theory to implementing tactical engineering solutions. The source material outlines 4 specific methods to improve judge reliability and mitigate these biases in production.
Okay, let's go through them. What's the first step?
The first step is utilizing structured rubrics.
Structured rubrics. I imagine I can't just throw a prompt that says, hey, is this a good answer, yes or no? Do I need to heavily constrain the output?
You have to define the operational boundaries completely. It means breaking down the evaluation into granular, clearly defined criteria within the system prompt. You do not ask for a general vibe check.
So what does the prompt actually look like?
You instruct the judge, score this response on the scale of 1 to 5, specifically for factual accuracy. Score it 1 to 5 for professional tone. Score it 1 to 5 for JSON formatting. And crucially, you must explicitly define the parameters for each integer.
So I have to write out exactly what a 1 means, what a 3 means, and what a 5 means for every single category.
Yes, you are narrowing the model's acceptable output space so it cannot fall back on lazy probabilistic biases.
And from an engineering standpoint, you wouldn't just ask for a free text response back either, right? You would use function calling or enforce a strict JSON schema so the API returns a structured object.
Right, like returning factual score 4, formatting score 5.
Exactly, because otherwise you're stuck writing chaotic regex scripts to parse paragraphs of text just to extract the final integer for your test suite, which defeats the whole purpose.
Precisely. You want programmatic interoperability. You need the output to feed directly into your continuous integration tools without breaking.
Okay, so a strict rubric with schema enforcement is step 1. But, even human graders struggle with rubrics if they haven't seen an example of a baseline good paper. Do we need to feed the judge historical data to calibrate its baseline?
Yes, which leads us to the second method, providing few-shot examples.
Few-shot examples, meaning we show it what to do.
Right. Before you ask the model to judge your new, unseen output, you inject examples of previous evaluations directly into the prompt's context window. You provide a bad response and demonstrate exactly how it should be scored based on the rubric, complete with the reasoning.
And then do the same for a good response.
Exactly. You provide a good response and do the same. You're essentially preloading the judge's attention mechanism with the gold standard of how you want the grading performed.
That mirrors how we prompt for generation anyway. Show, don't just tell. Establish the pattern so it can just continue the sequence.
Exactly right. Now, the third method is prompting for chain of thought reasoning. And this is arguably the most powerful tool for combating verbosity bias.
Chain of thought. So asking it to think step by step.
Yes. Instead of allowing the judge to just compute a final score and output an integer immediately, you force the model to generate its step-by-step reasoning before it outputs the final number.
I see the logic there. If it has to generate tokens explaining its rationale first, it's less likely to just blindly reward a long, fluffy answer.
Exactly. It forces the computational path to traverse the specific logic of the rubric.
Right. So it has to articulate why the fluff isn't actually answering the prompt before it commits to the final grade.
That is the exact mechanism. You're forcing the model to unroll its latent reasoning. By generating the analysis tokens first, those tokens become part of the context window, which then heavily conditions the final scoring token to be more accurate.
That is a really elegant workaround. And finally, what's the fourth fix?
The fourth fix addresses position bias through intelligent pairwise comparisons.
Intelligent pairwise comparisons. To beat position bias, do we just randomize the order of response A and response B across our test suite and hope the errors aggregate out to 0?
No, you can't just rely on randomization. You actually have to isolate the bias per evaluation. You swap them and run the test twice.
Oh, I see. So 2 distinct calls.
Yes. First, you run an API call asking the judge to compare A and B. Then, in a completely separate, isolated API call, you ask it to compare B and A.
And then you compare the results.
Right. If the judge picks Model 1's response in both scenarios, regardless of whether it was presented as the first or second option, then you have a high-confidence, unbiased evaluation.
And if it flips?
If the judge flips its answer based purely on the order, you know you either have a dead tie or you throw that specific evaluation out entirely because the judge is exhibiting position bias.
That is a highly pragmatic engineering workaround. You just want a bidirectional test and require consensus. But, even if I implement all of this strict JSON or rubrics, few-shot examples, forced chain of thought, and bidirectional, pairwise swapping our sources, emphasize something really critical before you put this into production. Calibration.
Yes, calibration is non-negotiable.
Like, you can't just set this pipeline up and trust it blindly, right?
No, you absolutely cannot.
Yeah.
The reality check here is that engineering teams must invest heavily in calibrating their LLM-Judge against human judgments before fully trusting the automated evaluation. You have to grade the grader.
Grade the grader. How does a team actually do that in practice?
You take a statistically significant sample, say 100 responses.
Mm-hmm.
You have your senior engineering team manually grade them against the rubric. Then you run your configured LLM-Judge over that exact same data set.
And you just look at the delta between the two.
Exactly. If the LLM-Judge aligns with your human team 85 or 90% of the time, then you have a calibrated judge. You can now trust it to run over 10,000 responses automatically.
Mm-hmm.
But until you mathematically prove that alignment, your CI/CD pipeline is basically flying blind.
I have to challenge that premise just a bit, though.
Yeah.
We just spent 10 minutes deconstructing how we need to build this massive, sophisticated infrastructure specifically to bypass the flaws and biases of LLMs. But the ultimate validation, the anchor for this whole system, is human judgment.
It is, yes.
Aren't humans incredibly biased too? I mean, we get tired, we misinterpret prompts, we have subjective preferences. Why are we treating human judgment as this flawless mathematical ground truth that the AI needs to align with?
It's a very valid pushback. Individual humans are deeply flawed and highly subjective. However, when we talk about a human baseline, we aren't talking about one tired engineer grading 100 outputs.
So what are we talking about?
The industry standard relies on aggregating human consensus to filter out individual noise. The human baseline is considered ground truth, not because it's mathematically perfect, but because the ultimate end user of these applications is human.
Ah, okay, the market reality.
Exactly. If an AI generates a response that mathematically perfectly answers a prompt, but a consensus of human users finds the tone grating or confusing, then it's a bad product. We calibrate the judge to human consensus because human preference is the actual market reality.
Okay, so it's about aligning the automated system with the messy reality of user perception. But if we still have to spend all these engineering hours meticulously grading things ourselves just to calibrate the judge, what is the actual return on investment here?
The ROI is massive.
But why go through the architectural headache to build an AI judge if we still need human consensus?
The ROI comes down to raw, unprecedented scale. Our sources highlight a critical economic metric here. LLM judges reduce evaluation costs by 10 to 100 times compared to human annotators.
Wow. Cutting costs by 2 orders of magnitude changes the math on literally everything.
It changes the entire software development lifecycle for AI. If you rely entirely on human evaluation, testing is a massive bottleneck. It's slow, and it's incredibly expensive.
So you'd only do it rarely.
Right. You might only be able to afford a comprehensive evaluation suite right before a major product launch or a major version bump. But with a calibrated LLM judge, testing becomes practically free and instantaneous. It allows for rapid, continuous integration.
So I can run my entire test suite on a random Tuesday morning.
You can run a full evaluation suite of 1,000 complex prompts on every single minor pull request. That level of iterative velocity is completely impossible if you were waiting on human annotators.
So it's not about replacing the human, it's about scaling the human's judgment. You spend your expensive human budget up front to define the architecture, write the rubric, and calibrate the judge.
Exactly. And then you let the machine apply that validated judgment 10,000 times over at a fraction of a cent per API call.
That makes total sense. You're front-loading the cost to unlock infinite automated scale.
Precisely. And we see this reliance on the human baseline reflected at the highest levels of the AI industry. The source material introduces Chatbot Arena as the prime example of this dynamic at work.
Chatbot Arena, for anyone listening who isn't refreshing the AI leaderboards every morning, how does Chatbot Arena actually function and why does it matter?
Chatbot Arena is currently recognized as the gold standard for foundational model evaluation. and it operates entirely on crowdsourced human pairwise comparisons.
So humans doing the A/B testing.
Exactly. They present a human user with two anonymous models side by side. The user enters a prompt of their choosing, both models generate an answer, and the human votes on which one is better based on their own subjective criteria.
Blind taste testing for LLMs.
Right. And based on hundreds of thousands of these blind human votes, the system uses an Elo rating system, the exact same statistical model used to rank players in chess or competitive video games, to rank the LLMs.
So if a smaller open source model consistently beats a massive proprietary model in blind human testing, it literally steals the larger model's Elo points.
It does. It's a continuous, brutally objective ladder match based entirely on human vibe checks.
And that's really the most trusted metric right now.
It is. The reason Chatbot Arena's Elo ranking has become the most trusted metric in the entire field, often more trusted than automated benchmark scores, is precisely because it relies on that aggregated human baseline.
Because benchmarks can be gamed, right?
Exactly. Automated benchmarks can be gamed, models can be trained on the test data, but you cannot game a blind human preference test at scale. So while LLM judges are absolutely essential for internal iterative development and unit testing, high-stakes decisions and the ultimate validation of a model's true capability still require that macro-level human oversight.
Okay, so we have this clear pipeline. Human judgment defines the standard. The LLM-Judge scales that standard to let engineers iterate cheaply and quickly. But, if we look at the broader trajectory here, evaluation isn't just a unit test at the end of the assembly line to see if the JSON is broken.
No, it's becoming much more than that.
Right. What we are evaluating actively shapes the core architecture of what we are building.
If we connect this engineering pipeline to the bigger picture of foundational model development, this is exactly where the technology is heading. Evaluation is no longer just a post-production QA task. It is becoming the foundational layer of how these models are trained in the first place.
Our sources preview this transition, moving from using the model as a post hoc evaluator to the evaluation process actually shaping the internal DNA of the model itself. How does that integration work technically?
It occurs through advanced training paradigms like RLHF reinforcement, learning from human feedback, and constitutional AI.
Okay, break the mechanics of that down for me. How does a judge model actively tutor a primary model during training?
Let's look at RLHF. You train a separate, secondary model called a reward model. This reward model is essentially a highly specialized, highly calibrated LLM judge.
Okay.
During the primary model's training loop, it generates thousands of potential responses. The reward model automatically grades them in real time, outputting scalar rewards, positive signals for good responses, and negative signals for bad ones.
Like a teacher standing over your shoulder while you do homework.
Exactly. And through an optimization algorithm like proximal policy optimization, the primary model literally updates its internal weights, its parameters, to maximize the score it gets from the judge. The judge's criteria backpropagate into the model's actual architecture.
So the test suite literally writes the code. Or, well, it writes the weight.
In a sense, yes. And constitutional AI takes this a step further. Instead of relying solely on massive data sets of human feedback to train that reward model, you give the judge model a constitution.
A constitution, like a legal document.
Like a strict set of rules or principles defined in text. Things like, do not generate instructions for illegal acts, or prioritize factual accuracy over helpfulness. The judge uses that text-based constitution to automatically evaluate and train the primary model.
That's wild. So the evaluation criteria literally become the permanent guardrails baked into the model's neural pathways.
They do.
The implications of that for an engineering team are massive. It means the judge you build today dictates the mind of the application you release tomorrow. Like, if your internal judge has verbosity bias during the reinforcement learning phase, you aren't just letting a few long answers slip into your production environment.
No, you're doing something much worse.
You are fundamentally altering the weights of your model to be a rambling mess.
Exactly. The biases of the evaluation system become the permanent, unalterable behavior of the creator system. It's an inescapable feedback loop.
Wow. That significantly raises the stakes on getting those JSON rubrics and baseline calibrations correct.
It absolutely does.
All right, as we wrap up this deep dive, let's synthesize the ultimate takeaway for you, the engineer listening to this right now, staring down your next deployment. If you want to build robust, reliable AI applications without burning through your company's entire runway on manual testing, you need scalable evaluation.
And LLM-as-Judge is your primary tool for that.
Right. It's your 10 to 100x cheaper shortcut to running thousands of test cases on every single pull request. But as we've explored, you cannot just trust the API blindly. You have to actively engineer against the architecture's innate flaws.
The verbosity bias, the attention mechanism-driven position bias.
Exactly. You have to constrain the output with strict JSON rubrics. You must force chain of thought reasoning before scoring. You have to run bidirectional pairwise comparisons. And above all, you have to spend the engineering hours doing the human calibration up front. You have to mathematically prove that your automated grader actually aligns with reality.
It requires applying a rigorous, deterministic engineering mindset to a highly stochastic, probabilistic problem. But, as we discussed with RLHF, the implications go far beyond just testing for broken JSON. This paradigm shift raises an important, arguably systemic question for anyone building foundational AI architecture.
Yeah, so what is the lingering thought they should be chewing on during their next late-night coding session?
Think about the trajectory of the tech stack we just outlined. We are rapidly moving towards systems like constitutional AI, where AI evaluates AI at massive scale, and those automated evaluations dictate the literal parameter weights of future models.
Right, the AI tutors the AI.
Yes. So if the industry relies increasingly on LLMs to judge other LLMs, bypassing the human bottleneck entirely for the sake of velocity, are we risking an eventual architectural echo chamber? A future where models only optimize for the latent space patterns that other machine models prefer, slowly but surely drifting away from the messy, subjective, and nuanced reality of what actual humans value.
An automated echo chamber where the AI is just aggressively optimizing to impress other AI and leaves user preference out of the loop entirely. Man, that is a thought that will definitely keep you awake while you watch your CI/CD pipeline run. Thank you for joining us on this deep dive. Keep questioning the testing systems you build, keep calibrating your judges to reality, and good luck with that next pull request. We'll catch you next time.